Welcome to week 7. You've made it this far. Pats on the back, yes. And tonight we're starting radiology. So Sarah was mentioning she had a day. It's just about to get better, Sarah, I promise. I know. All right. So we're going to start by talking about the certification exam. Getting some questions about that out of the way, and then we're going to dive right into Chapter 15. Hopefully you have had a chance to read it. And, okay. All right, so radiology is the study of radiation, especially for the use and diagnosis and treatment of disease. So we use dental x-rays every day in the dental office. And so this is a huge part of what we do as dental assistants. And we are going to begin with safety and how x-rays are made, which is the foundation for the certification exam. So what is the certification exam? We've talked about it a little bit, but let's talk about it again. RHS stands for Radiation Health and Safety. And it is administered by Danby. So it's a national test. Which means that all dental assistants who are RHS certified take the same test all throughout the nation. It is a computerized multiple choice test, and there are only 2 centers in Maine that you can take it at. You can either take it in Bangor or in Westbrook. So there's not a lot of choice, especially for those of you who are far-flung on where you go. But if you are a military spouse or in the military, you can take it on a base. And so I have a link there just in case that applies to you, and you can click on that to schedule. The test is pass-fail, so you are notified right away after your test whether you pass or fail. Scoring is set by how difficult the question is, not by how many you have correct. And this is kind of a weird thing for most exams because what RHS does, is it looks for your weaknesses and it exploits them. It's smart. So what it does is, if let's say I get a question wrong, it's going to ask me another question that's similar on the same kind of content to see if I really don't know it or if I just didn't understand the question before it. So what it does is kind of push you in many different directions to sort of see how much you know about the basics of radiology. And so in Maine, with a passing grade on the RHS, you then can apply for your dental radiographer license because Maine requires a license on top of the RHS exam. So that's why this part of the course is so important, because it's that thing that determines how useful you can be in the dental office. For those who are watching from Illinois, Georgia, and Alabama, hello, ladies and gents. You do not require any additional licensing. So once you pass RHS, you're good to go. So in Maine, extra tests. Now, the rules on this are different for every state. So if you think you want to move, you want to look into sort of the state that you're going to, because every state has different regulations for dental assistants. Okay, so it's 100 multiple choice questions, and there is an hour and a quarter for testing time. So that is, 75 minutes. And that means that you have 75 minutes to do 100 questions. So that's kind of scary because it means that that's less than a minute a question. But many of the questions, if you're prepared well, should come to you very quickly, and then you move on. I had plenty of extra time at the end of my test, and I think you will too. In general, it tends to go pretty smoothly. So how do we prepare? The first thing we do is we do the Dale Foundation Review course, which you will have access to for 6 months. So when you are ready to begin your studying, send me an email that you're ready for Dale, and I will send it to the school. And then you will have access to the Dale Foundation for 6 months. It's an online sort of testing program that you can continue to practice with. And you want to have an exam grade higher than 70 for chapters 15 and 16 before you get the Dale Foundation. So the Dale Foundation is not meant to teach you, it's meant to review you. So you want to make sure that you're most of the way there by the time you're ready for Dale. Once it's ordered, you'll get a time-sensitive email that you have to open within 7 days to begin that 6-month access. And that's probably the hardest part for everybody, is making sure that they log on within that week. So Dale Foundation is just a review tool that you've already paid for in your tuition.
And it goes toward the RHS.
It helps you study.
Okay.
Yep. All right. So when you continue to prepare using Dale, and there are also some more review materials on Evolve, and when you feel almost ready to take this big RHS exam, is when you are going to fill out your application. So, oops, wrong way. So the RHS exam application packet is on Evolve under course content, Danby RHS Radiation Health and Safety Exam. There is an application in that folder that you're going to print out. You're going to fill the whole thing out except for the payment section because you have already paid for the exam. And you're going to send it to the school or to me, either way, by email. So when you fill out the application, you'll see on the bottom it says fax to Danby. You don't want to do that because you've already paid for it. So you're going to either send it to me or send it to the school, and then we will apply to Danby to take the exam. So when you're filling out this application, there's a bunch of instructions on Evolve on how to do it. But the biggest thing is that your name has to exactly match your ID, because that's how they let you into the testing center. So if your name is different than what they have on the test notice, then they won't let you in. So 2 to 4 weeks after that application gets to Danby, they are going to send you either an email or a snail mail admission notice. And that's when you can schedule your exam. So you have 60 days from the time that you get your test notice to schedule this exam. So there are many different steps to this, and everybody gets confused about what step am I supposed to be doing now, which is why I have it all at the beginning of this. So when you think you're confused, make sure to go back to the beginning of tonight's lecture to run through it. And then if you still have questions, obviously, just reach out and I will help you. So lots of stuff there. So who schedules the exam? You do. So you get to choose your time. You get to choose your location. I know there's only 2 choices. All right. So what content makes up the RHS exam? 31% of it is on radiation safety for patients and operators, which is where we're going to start tonight. 26% is on exposing and evaluating. 22% is on infection control for radiology. And 21% is quality assurance and radiology regulations. So remember, this is all multiple choice. So there's no technical part to this. So you don't have to have ever taken an x-ray to be able to pass this test, which is a good thing, right?
Yes.
Especially for us because we're all online babies. All right. So what do? You stay awake, you pay attention, you ask questions, you read the book, you learn the material, you don't cram, you prepare for tests, and you do not give up. If I could give you any advice, that would be my biggest one, is don't give up. Because it's so easy, isn't it, to just be like, ugh. Yep. But it's not, you've already paid for this. Maximize it. Get that certificate. The certificate never expires. But if you want to move on to the next level of dental assistant, which is CDA, you want to do that within 5 years, or else you'll have to take the test again. All right. So questions right now about the RHS test itself, or the application procedures, or Dale Foundation? No?
So I email you.
Yep.
Saying I want to do the
Dale. Yep.
The Dale test.
Yep.
Okay.
And then you have access to that for 6 months to keep studying. Yep. Okay. When you think
so
you're
Yep.
When you think you're mostly ready is when you want to start to fill out the application for the actual exam.
Okay.
So because there's only a couple weeks between when they receive the application and when you're ready to schedule it, I tell people to make sure that they've done some studying before they apply.
Yes.
Yeah.
Okay.
Yeah. So
I have a question.
go for it.
Do you have any other tips in helping to study?
I have tons. Yes. I actually have a whole folder on Evolve in that RHS folder full of materials that I have collected that have helped people pass in the past. I have personally sent probably more than 100 students for this exam, and I have really good pass rates. So it's mostly making sure that you can answer the questions as we go through this. So when you feel yourself like not keeping up with what we're doing, especially in class, that's when you want to make some notes to say, go back over this part. Make sure you go back over this. In the past, I have offered a review class, but nobody really likes to take me up on it because they find that their study is usually better spent by themselves. But I still will offer that. If anybody wants me to do a review class, I'd be happy to do that. So, yeah, there are not too many shortcuts for this. So, study, and read.
Thank you.
Yeah, you're welcome. So I'll tell you before we get into this, I'll tell you a story a little bit. I know I'm full of stories. But I passed probably, 10 tests on radiology and had no idea what I was doing until I started teaching it. So, yeah. So I had trouble. Radiology is a lot of chemistry and a lot of physics. And I had trouble with both of those subjects in school. And, I got, B's and enough to get me into dental school and pass. But it wasn't my strong suit. And so I took a bunch of tests on radiology when I was a dental assistant, when I was in dental school, and I never understood it. I was mostly guessing and going by what I did learn through it. And when I first started teaching about 8 years ago was the first time that I actually understood. It was like, oh, that's what they were talking about. So you do not have to understand it to the level that I do to be able to pass it. But you want to try and meet me as close as you can because the more you have, the easier it will be for you. All right. So here we go. If there are no more questions. All right. So our learning objectives. I have a link here, and I'm just going to click on it quickly just to show you. It's already open. I have all of the learning objectives in a question and answer format, which is going to be really useful when you are trying to see, do you understand this or don't you? All right. So this will be posted on Evolve along with all of the objectives here. So we'll go through these real quick. Okay. So why do we talk about dental images? Well, of course, they're essential for our dental practice. Most of the diseases that are in the mouth cannot be seen just by looking. We have to look using imaging techniques. And they are either produced using film or digital technology. Now, for most of your offices, you're going to have digital, but there are still some holdouts out there that are using regular x-rays. And they are also still testing us on the regular x-ray technology. So we have to be versed in both digital and conventional right now. So radiation has the ability to cause damage to all types of living tissue. And any exposure to radiation, no matter how small it is, can cause harm to a patient and to ourselves as the operator. But the benefits of using x-rays outweigh the risks of using them. And we're going to get into that concept just a little bit more. So what do we use them for? We use them to detect dental decay, so that's the biggest thing, and to identify bone loss in the early stages. So the first two things that we use dental x-rays for are to detect caries and periodontal disease, the two main reasons that patients come in to see us. All right. So why do we use x-rays? Because it helps us to find decay and find periodontal disease or bone loss. So we locate abnormalities in the hard and soft tissue, and by abnormalities we mean cysts and tumors. We evaluate growth and development with x-rays. So if a patient is going to have braces put on, they need x-rays to be able to measure their growth and development. We document baseline for a patient. So if you take x-rays on me today, then you know what changes have occurred 5 years from now by looking back. And that's important because we always want to be able to compare one thing to another to make judgments. And they are also used during dental procedures, like root canals. We use them to visualize the bottom of the tooth because that's not visible when we are just looking in the mouth. Or we use them to find broken root tips during surgery, or foreign objects that may be pushed into the bone or into the soft tissue. Yeah. So what do we want to take away from this? Any amount of radiation, no matter how small, can cause a biologic change in a person. And we say, though, so why do we use radiation if it's harmful? Because the benefits outweigh the risk of not knowing. So when we use x-rays safely, when we use radiation safely, the benefit of diagnosing the patient outweighs the risk of harm. And so quality images are needed every time we take a film to be able to identify and diagnose something that might otherwise go undetected. And we use either film or a computer to produce these images. And again, any amount of radiation, no matter how small, has the potential to harm both the patient and the operator. So when we begin to learn about x-rays, what we have to do is take ourselves out of the patient chair and put ourselves into the operator position. So we are the operators because we're the person taking the film.
I have a question.
Absolutely.
How do they do it on computer?
We will learn.
Oh, okay.
Yeah, that's a great question. And it's part of where we're going. Okay. So, yep. So this is just an illustration of that risk versus benefit. And so we say that the benefit outweighs the risk. All right. So the diagnosis from an x-ray provides more benefit to the patient than it does a risk to them from radiation. All right. So let's get into some physics, which feel free to cry. It's okay. I remember. So we need to understand basically how x-rays are made so that we can practice safely and produce the best quality image. Now, here's the thing. When you go to make toast, nobody says to you, tell me how that toaster works, right? Mm-hmm. All you know is you push a button and it works. Mm-hmm. But with x-rays, you also need to know what's happening inside of the machine when you push the button. Okay. So nobody tells you this going in, that you're going to have to learn a little bit about electronics, but you do. So what is the definition of an x-ray? An x-ray is a weightless bundle of energy that is called a photon that does not have an electrical charge, and it travels in waves at the speed of light. So you cannot see x-rays because they travel at the speed of light. You cannot hear them. You cannot feel them. You cannot smell them because they have no weight. They have nothing to them, basically. So we could be being exposed to x-rays right now and would never know it. Okay. All right. So they clear a room faster than you can blink because they travel at the speed of light. And they also cause certain substances to glow or fluoresce. And that is a property that is important both to their discovery and also to their uses today. All right, so here's our physics review. Energy and matter. All right, so energy and matter make up the whole world. All right. So we have energy stored inside of us, and we are made of matter. So the whole world is made up of energy and matter. Energy is part of, and X-rays are part of electromagnetic radiation. So X-rays are like radio waves, TV waves, cell phone waves, microwaves, radar waves, ultraviolet light, visible light, the light from the sun, cancer therapies. These are all examples of the same types of energy waves that X-rays are. But for some reason, when we start talking about X-rays, everybody's mind goes, nope, never heard of it, can't do it. Now, I don't pretend to know anything about radio waves or TV waves, but I understand that there are radio waves that I pick up when I am tuning a radio. All right? And so I know they're there even if I can't see them. Which ones can we see? Well, we can see ultraviolet light. We can see visible light. We can see the sun. Yep. But that's about it. So a very small part of energy can be seen or is visible. The rest of it's all invisible, like X-rays. And they all travel in waves. And when I say they travel in waves, what I mean is they do this. Mm-hmm. All right? So the next thing to review or to remember is that matter is anything that has weight and takes up space. So matter is made up of a million little atoms, which we cannot see. All right? So this table, my skin, millions of little pieces that I'll never be able to see with the naked eye. But get enough of them together, and then we can see them, right? So they have space and have weight, whereas energy does not. The atom, which is what makes up all matter, has important parts. In the middle, it has a nucleus with protons and neutrons, and on the edges, electrons rotate around. And atoms join together to form molecules, and then molecules can eventually be seen, like water. And so this is my favorite meme on matter and energy. So you matter, unless you multiply yourself by the speed of light squared, then you energy. All right? So they relate to each other, but they are not the same, right? Thank you, Einstein, for that. All right. So here's a picture of the atom. And for many of you, this brings back horrifying days of high school, right? So we're going to try and break it down so that we understand why on earth we're studying it now. So around the atom, around the nucleus of the atom, are electron shells that have electrons in them. And the K shell is the one that is closest to the nucleus. So if you look at this diagram, let me get my pointer, you can see that this is the K shell here, this light blue one, and it is the one that is closest to the center. And atoms are like football players holding footballs. And the tighter they hold the football, the less chance that it will come off, right? But somebody who's running with a football and they got it way out here, really easy, sorry, you can't see my arms, way out here, really easy to pop that football off, right? To get it out of the person's arms. So electrons, when they are held tight to the center of the atom, are very difficult to move, hard to get off of the atom. But ones that are on the outside are very easy to get off. So if we look at this, we say that the K shell electrons are tighter to the atom and harder to remove from the atom than the Q ones, which are way out here. So Q is easy to pop off, K not so much. Okay, so the K shell is the closest to the nucleus and it has the highest binding energy, meaning that the electron is held tightly and we're going to have a hard time getting it off of that atom. Now, why would you want to take it off the atom? That's something that we'll have to figure out in a minute. So if we have two hydrogen atoms and one oxygen atom, they have to go together in a certain way. And they have a certain number of protons and a certain number of neutrons. So hydrogen, I think, has 1, and oxygen has 8, and has the same number of electrons, and now we all want to cry, right? So those things are not as important as understanding that the electrons are the key to how these things fit together. So oxygen and hydrogen are sharing these two negatively charged particles, the electrons.
Oh, okay.
All right? So without this sharing of these negatively charged particles, you don't have water.
Right.
So that has to be important, right? Because
Absolutely.
humans are almost 80% water.
We need water.
Yes, and we need water to live. So if we couldn't share electrons between hydrogen and oxygen, we would not have water. All right? So that's why that's important. Why is it important to radiology? Hold on one moment. All right? So let's talk a little bit more about energy itself. So the radio waves, the microwaves, the infrared waves, these are all down here on the low energy side of things. They are long wavelengths, which means that they move really slowly. And they're low frequency, which means that not a lot of them are going to happen in a period of time. All right? But up here, where the X-ray is, you can see that these have really short wavelengths, high energy, and high frequency. They're moving quickly. All right? This moving quickly is what allows them to penetrate matter, to go through and eventually produce an image. All right? The fact that they have more energy than these do down here makes them stronger. Okay? And then gamma rays up here, this is nuclear energy, and also the radiation that's used to treat cancers. All right? So that's stronger than X-ray is. And X-ray is stronger than the sun, and the sun is stronger than visible light. Mm-hmm. You see how it works? Visible light is stronger than a microwave.
Yeah.
All right? And this is how it works. So these things are called electromagnetic radiation. They're all the same, except that they move with different amounts of energy.
Okay.
All right? Okay. So to go back to our water molecule and our matter, if all of a sudden this water molecule stops sharing these electrons, I won't have water anymore.
No.
Does that make sense?
Yeah, you just have the.
Right. You'd have pieces of the water,
Yeah.
but not the water itself. And of course, you can't sustain life on that. Mm-hmm. X-rays cause those molecules of water and any type of matter to give up some of their electrons.
Okay.
And so therefore, they are no longer that stable water molecule that we need. Mm-hmm. They become unstable, and they go looking around for something else to bang into. Mm-hmm. And most of the time, especially in the case of water, that something else that they look around to bang into is not a good thing. Mm-hmm. So when an X-ray goes through a person, a molecule of water can be broken apart and turn into hydrogen peroxide. Mm-hmm. And hydrogen peroxide, my friends, is not good for you. No. All right? It might be good in a short term, mm-hmm. but it doesn't do what water does, right? Right? So once you split these molecules apart, they're no longer the way they used to be, and they can't do their job. And that is what causes the problem between X-rays and humans, or radiation and humans, is ionization. So what is ionization? Ionization is when an electron is popped off of a stable atom, causing it to become unstable and look for a new partner. So this can happen to solids, it can happen to liquids like water, and it can happen to gases as well. The problem arises when it happens to humans. So if an atom gains an electron, it becomes a negatively charged particle. If it loses one, it becomes positively charged. And let's look at this in hopefully in a form that we can wrap our heads around. So here's some water, and here are some X-ray photons. And what does X-ray do to water or to any matter? It ionizes. All right, so the name of the process that X-rays cause to matter is called ionization. All right, what that results in is a splitting up of the water. And this is called free radicals. And if you've ever bought any face cream, you see on the jar it says prevents free radical formation. Right?
Yeah.
Isn't that why we buy all those things? To make ourselves beautiful? Right?
Yeah.
Free radicals combine together to form a toxin such as hydrogen peroxide, which is not good for you. It causes wrinkles or redness. And over a long period of time, it can cause cancer. So, why are X-rays bad for humans? Because they ionize our makeup, our matter, our atoms, and turn them into negatively and positively charged particles, which then
Free radical.
can cause problems. Yes.
So if it's going on for too long, it's going to cause a problem.
Yes.
Okay.
Yep. So why do we get wrinkles by being in the sun?
Yeah.
Because this process is happening there too. All right. So the beauty industry has built $1 million industry, right? $1 billion industry around the fact that free radicals cause wrinkles.
Yeah.
So ionized atoms are lacking a full electron, and they're looking to steal from others. And when they do, they don't always come back to form water. They come back to form other things as well. So let me give you a little analogy, tell you how I think about this. So I think about water as being like the happy home. And then all of a sudden an X-ray comes along, and X-ray is the side chick. So here's my happy home. Side chick comes along. I find out about it. And now we've got 3 people who are not happy.
Okay.
All right? We've got the man who's by himself. We got me, and I got the kid, so I'm an OH. And then we got the side chick. All right? Now, sometimes they come together, right? But sometimes they don't. And you may be left with a whole bunch of broken pieces. And those broken pieces are then going to go out and wreck other people because they're broken.
Right.
All right, so that's the way I like to make it make sense to myself. It certainly has nothing to do with physics. All right, but it helps me to understand that split or that breakup of the atom. All right. Okay. Questions on the physics? Not so much yet. All righty. We're going to go into some more properties of X-rays. Now, we've already said these, but we're going to say them again. Okay? So, because X-rays travel in waves. Apparently, Elmer Fudd is teaching your class this evening. Has a short, the higher energy waves have a short wavelength. Short wavelength, high energy waves pass through the tissue much more quickly and cause less damage. So we like X-rays that go quickly and will pass right through. What we don't like are X-rays that have low energy and long wavelength, because they're going to come and get stuck inside. They're not going to have the energy to pass through. So when it comes to X-rays, we like them short and high. We do not like them long and low. All right? And this is something that you can say to yourself, and then when you get a question on RHS that says, which waves cause less damage to humans, you're going to be able to say short wavelength, high frequency, because we like them short and high.
Right.
All right? So this is what mnemonics do, and mnemonics will save your life when it comes to radiation. All right? They travel in straight lines, which means they cannot go around corners. So you can hide from an X-ray really easily. So as an operator, that's a great thing to know. Because if my X-ray is going this way, all I have to do is stand over here. Right? Because it doesn't know how to make a curve. It's only going that way.
Okay.
All right. So that cannot make turns or go around corners is important to know. They travel at the speed of light. So faster than I can blink, they're gone. So if I take an X-ray as an operator, do I have to wait before I go back in the room? Nope, I don't. Because they go instantly. They go away. They have no mass or weight, so they're not positively charged or negatively charged. They have no feeling to them, and they cause some substances to fluoresce or glow. And I'm going to stop here for just a second and talk about how X-rays were discovered. Now, we talked about a little bit about this in our very first lecture, about how Wilhelm Conrad Röntgen was in his laboratory late at night, and he was experimenting with waves. And across the room, a green screen started to glow. And so he knew that he had found a new wave. And he called it the X-ray because X stands for unknown in math. All right? So all this time, you've said, I'll never use algebra again, but the X-ray is the unknown. It's the unknown ray, all right? And we've called it that ever since because that's what he named it, all right? So when X-rays were first in use in dentistry, it was about the turn of the century. So they were discovered in 1865 or 1864, something like that. I forget whether it's 4 or 5. Don't kill me. And they were immediately, he began taking pictures. And one of the first things that he imaged on the human body was his wife's hand. All right. And so there's a very famous picture that shows her ring in the X-ray. Yeah. And so we didn't know that X-rays were harmful then. All we knew was that we could see inside a person. And so one of the, I think that she is quoted with saying, I have seen my own death when she had the X-ray of her hand, because no one had ever seen the inside of a human body before that way. All right.
It was scary.
Yeah, so it was frightening for many people. Yeah. But by the 1920s, they were using these things called fluoroscopes in shoe stores, where you would put your leg in, and it would take an X-ray of your leg to make a perfect fit for a shoe.
Oh, wow.
Do you think that's a good idea?
No.
No, because X-rays are harmful. But we didn't know this, so we were using them for everything because we thought it was really neat. All right, so the most famous dentist that we know, who was the first one to hire a dental assistant, is Edmund Kells. All right. Yep. So Edmund Kells was a pioneer in using dental radiographs, and he took the first film on a human for diagnostic purposes in dentistry. But he lost his finger from radiation, and then his hand, and then his arm, and eventually he committed suicide because he didn't want to be a burden to his family. A dentist with one arm, I can imagine,
Yeah, I was just going to say.
does not have much to look forward to. Yep.
How would he
Yep.
practice?
Yeah, so he killed himself. So there have been many people who sacrificed in the name of science so that we know what we know today. So using that story, just kind of remember as you're going through this that you don't want to sort of discard the knowledge that has taken, like, when I look at this and I think, oh gosh, I hate this stuff, people have died to make sure that we know it. All right, so that's the end of my preaching. Okay, let's talk about radiation. The types of radiation that we see in the dental office, that we expose our patients to daily when we use X-rays. So primary radiation is what comes from the X-ray tube head. So the thing that they put up to your face to take the X-ray, that emits primary radiation. And so it's what you shoot at the patient. It's like a bullet. Secondary radiation is like a bullet bouncing around inside the body. So as soon as I've shot the bullet from my radiation, that radiation bounces around inside the tissue, causing damage to my patient. Scatter radiation is like the bullet and the blood that have exited the patient. They've already gone through the patient and they make a spray on the wall or something like that. So if we think about radiation being like a murder scene, all right, we've got the bullet bouncing around in the body, we've got the bullet exiting the body. This is what radiation does, except it's invisible. We can't see it. So damage is being caused by the secondary, by the scatter. The only reason that we use the X-ray is for the primary radiation, to make the image on the film. But we end up with these two leftovers as well. All right? Scatter radiation harms both the patient and the operator and anybody else in its path. So this is why when you have a dental X-ray taken, the person taking it runs out of the room to press the button and leaves you there by yourself, is because the scatter radiation can also harm the person taking the X-ray. So leakage radiation is like a bullet that escapes when the safety is off and you don't mean to fire it. Leakage comes from the tube itself. So the machine, if it's leaky, could also be leaking radiation. All right, so here's a visual of this, okay? So the primary beam is the blue. It's the reason I'm using this whole process. The secondary beam is what comes out and goes around inside the patient. The scatter is what ends up coming outside of the patient. Doesn't get stuck in, but can also harm me as well. So how do we measure radiation? How do we measure what we can't see? We have two standards, kind of like miles and kilometers. We have the traditional, which is like miles, and the SI system, which is System International, like kilometers. So the traditional system has Roentgens, rads, and REMS. These are the three ways that we measure radiation. Their counterparts in the SI system are coulombs, grays, and sieverts. So radiation that someone is exposed to is measured in Roentgens or coulombs per kilogram. The dose absorbed by the tissue is measured in grays or rads, and equivalence between types of radiation, which measures the effect it has on a human, is measured in either REMS or sieverts. So what we typically have to do is know if I give you a REM, what's the conversion? The conversion is sieverts. And actually just like using the traditional and SI systems, there's usually something you can multiply by to get there. But that will come later.
So you need to know the conversion?
You might want to add in some of those numbers, but not yet. And we'll talk about them later. So for right now, we want to know that radiation is measured, and it's measured in two systems, traditional and System International, and then the three types of each. So how much radiation can a person safely get is called an MPD, or a maximum permissible dose. And this is set by the National Council of Radiation Protection, or the NCRP. And what it does is it tells us per year how much we can get without noticeable effect. So we've already said that no matter how much radiation you get, changes do occur. But there is a point that the human body can recover from. So if you work with radiation, you are called occupationally exposed. So as dental assistants, we would all be occupationally exposed to radiation. And we can get 5 REMS or 0.05 sieverts per year. All right? So the conversion between the two is a factor of 1/100th. All right? But I don't want to play with those numbers. They make me cry. So math makes me cry in general. So I memorize 5 REMS, 0.05 sieverts. All right? That's my MPD as a dental assistant. Now, if I'm pregnant, I can't get hardly any. I can only get 0.05 REMS or 0.005 sieverts, all right, during the pregnancy. If I am in the waiting room I'm the general public, I don't work with radiation, and I'm not the patient, I can only get 0.1 REMS or 0.001 sieverts per year. All radiographers, however, can and should strive to get 0 MPD. All right, so we say, well, I can get 5 REMS. You don't want 5 REMS, you want none, right? Because radiation is harmful. So what we're going to learn is how to keep our patient's exposure low and how to keep our own exposure at 0. Excuse me. Okay. So, where do we get radiation from? What sources are there? Radiation comes from the ground. It comes from space. It comes from some of the foods we eat. We get it when we are patients ourselves. We get it from microwaves. We get it from radios. We get it from cell phones. And we could get it from weaponry or nuclear power plants, nuclear energy, things like that. But the point is, you're always exposed to radiation. And radiation is worse in some areas of the world than it is in others. So if you live in Denver, you get the equivalent of having 5 full sets of x-rays a year just by living in Denver compared to living in Boston. Anybody know why that is?
No.
Because Denver is a mile closer to the sun.
Oh, wow.
So you get more radiation the closer to the sun you are than not. If you live in Brazil, you get the equivalent of having, I think it's like a full set of x-rays every day for a year, more than you would living in Boston. And that's because of being so close to the equator and more sunlight. So it all depends on where you live and the things that are around you as to how much radiation you get. But that's something to know along with being an operator of x-rays, is that you're still being exposed to radiation. So how much radiation can a patient safely get? For every state in the U.S., we say ALARA. And ALARA means as low as reasonably achievable. It means that the benefit to the patient outweighs the risk of not knowing what the condition is that the patient might have. So what's the answer? As long as the radiation received by you as a patient or a patient is diagnostic, there is no limit. So that means if you need the x-ray, you should have it. But if you don't need it, you shouldn't. All right? So you think about this, you can say, well, I broke my leg, and they had to take a lot of x-rays, so I don't want to have a dental x-ray taken. But what is the risk of not having that x-ray taken? It could be that you have a cavity and that you could cause yourself 6 months of pain and disease by not having that one x-ray. All right, so this is what we weigh all the time when we talk about, are we taking x-rays or are we not on our patients?
Kelly?
Yes.
So, in some circumstances, someone could have a broken leg and be exposed to radiation and then find out that, something worse comes of it.
Yes.
That happens often.
Yep. So, for instance, let's say, and I've had patients like this who have had many CAT scans to find a cancer, and then they have had radiation treatment. And so you can imagine how they feel about their own exposure to radiation at that point in a year. And then they come into the dental office and we say, okay, we're going to take a couple x-rays. And they go, oh, no. No x-rays for me. I've already had all the radiation I can stand this year.
Yeah.
Right? But what we can do to discuss with our patients is whether it would be worse to not have those films than it would be to take them. So are we being irresponsible if we say, oh, no, you should have them? Not all the time. So if the patient doesn't have any visible decay and no problems, they may be able to wait 6 months. Because radiation exposure is cumulative. It adds up. And if you can give your body a rest to recover from it, then we can take the films in 6 months. All right, but that doesn't work for everybody. Some patients need them right then. So what if that patient who has had the CAT scans and the cancer radiation treatment has a toothache? They're going to need that x-ray because we can't treat without it. So those are the things that we weigh. Does that answer your question?
Yes, thanks.
Yeah. Okay.
Yeah.
Okay. So what exactly does it do to the body? It can change your chemicals, your tissues, your organs, and your cells. And the time from exposure to radiation to symptoms is called latent period. Acute exposure is a large dose in a really short period of time. And an example of that is a nuclear accident. And so in 1986 in Russia, there was an accident with the Chernobyl nuclear power plant. And there are some really good YouTube videos on this that sort of help you to understand what a large dose in a short period of time does. It's basically fatal in most cases.
How do you spell that, Chernobyl?
Chernobyl, CHERNOBYL. Yep. And I'll actually, I can put the link up. Okay. I'll put the link up because it's really interesting. But large dose, short time is not good. Yeah. Okay. Now, chronic exposure is a low dose over a long time, and that's not good either, right? So being exposed to a low dose over a very long period of time is not great for the body either. But that's a chronic exposure. And what happens is it will change your body cells, which we call somatic damage, or it can change your genetic cells, meaning changes your egg and sperm. Wow. So you're not harmed in the case of genetic damage, but who is? Your offspring. Mm-hmm. Your babies. Mm-hmm. So somatic problems don't get passed on to the next generation. So if I have a tumor on my arm from radiation, my son won't. Mm-hmm. But if my egg or sperm is damaged before I have children, then my son or daughter would have damage.
Okay. Yeah.
And we've seen this again. We just want to remind ourselves, because we are 80% water, that this is a real thing when it comes to radiation and human beings. Not all tissues in the body are equally sensitive to radiation, though. Some are more sensitive than others. So this goes from very high to low sensitivity. Now, the lowest sensitivity in the body is mature muscle and nerve cells. So your bones, your mature muscles, your mature nerves don't really react that much to radiation. What does react are the small lymphocytes, which are immune cells. And your bone marrow, your reproductive cells, and the inside of your intestines, the mucosa of your intestines. So basically, anything, cells that divide more often, cells that are more active, are much more sensitive to radiation than cells that are not. The exception being reproductive cells, because they don't divide at all until they are fertilized, but they are very sensitive to radiation. So what we look at from this whole list are which things on this list does dentistry actually contact. Because if I'm taking an x-ray of your tooth, I shouldn't be anywhere near your genetic cells. Right. Does that make sense? Right? So what I don't know why there isn't one. I'm sure it's somewhere here. But what we do touch, bone marrow, because there is bone marrow in your lower jaw. Skin, because the skin of the face, right? We go through that. Some films will catch the lens of the eye and the oral mucosa, and of course your connective tissue, some small blood vessels, and depending on the age of the patient, bone and cartilage. And then the thyroid gland, which is in your neck. All right, so that gets it too. And we'll have a list of those somewhere. I don't know where it is, but it's here somewhere. So how do we protect our patients from all of these things that we're learning about? So how do you keep a patient from exposure to radiation to their blood forming or reproductive organs? Well, you put a lead apron on them. So the lead apron minimizes or eliminates the genetic and somatic effects to the center of the body.
Well, hi there. Nobody in there. It's dark.
Oh. Oh my. I thought there was somebody there. That's weird.
Wow. What did she say?
She said nobody in there. It's dark. Oh, I get it. Okay. So the thyroid collar is also what has to be used. Thyroid collar is used for all intraoral exposures. So anytime we take an x-ray inside of a patient's mouth, they need to have the thyroid collar on. Children are especially sensitive to this, and it may be attached to the lead apron or it may be a separate piece. But it is not used when we're taking x-rays outside the mouth, which we're going to see. Okay, they left. All right. We reduce the number of films, and we take only those that are prescribed by the dentist based on patient need. So we should never be taking x-rays just because you're due for them. We should be taking them because we need to see whether there is something there or there isn't. All right. So sometimes you may have heard that phrase when you go in. You're due for your x-rays, which could probably be said a lot better, as in, you have not had a cavity check in 2 years and we need to check for decay. Mm-hmm. All right. That's a better way to say that than to assume that everybody needs them at the same time. We also reduce retakes by using proper technique, making sure that we expose properly and carefully. And then we use beam alignment devices to line up the x-ray beam with the film to eliminate errors. All right. And here's some visuals of this. So, lead apron with the thyroid collar. All right. Now, these lead aprons down here, including the one on the teddy bear, do not have thyroid collars on them. All right. And this is because these are going to be used for x-rays that are taken outside the mouth, not inside the mouth. And we'll see what those are in the next slides. Sorry. Film holders are up here. All right. So what these do is they align the beam. You can see how this is shaped round like the cone here. Mm-hmm. They align the x-ray with the film or the sensor, the digital sensor, so that we get the best possible image each time. And that also eliminates the patient from having to hold it. And then you can see here, this is a student taking an x-ray on a dummy, because dummies are very forgiving. They don't care how many you take because they won't get cancer from them. And that's how it works, is we line up the circle to the circle. So I like to call these idiot rings, and not because we're idiots for using them, but because it's nearly impossible to miss if you can line up circle to circle. All right. Now, remember that when you actually take your first x-ray, because you're going to be like, this is harder than it looks. It is. It's a lot harder than it looks. So I say that sort of the idiot ring as a tongue-in-cheek, because taking x-rays is hard, no matter whether you have a film holder or you don't. And that's because patients, they have cheeks and stuff like that, can't seem to get rid of them. All right. So more protection of the patient. Use fast F-speed film. All right. So we have different film speeds, and D and E are so yesterday. They're slow. So we're going to use F-speed or fast film because it requires 20% less radiation than D or E speed. What makes it fast? Larger crystals on the film. What does that mean? I have no idea yet. All right, no, I do. But I don't want you to have any idea yet. what I want you to have an idea of is fast film has larger crystals, whatever the heck those are.
Okay.
All right. So the other way to protect your patient is to use digital. 70 to 80% reduction in radiation when digital is used. So computerized radiology, digital radiology, needs less radiation than film does. Reduce exposure with features that are built into the machine. So this you can't control, but you need to know those features and how they work. Why? I don't know. It's like somebody said, nobody asked me when I made toast how it worked. I don't know. I just pushed a button. All right. But with x-rays, we have to know. So in an aluminum filter, we'll filter out the long and low wavelength x-rays. So remember we said long and low are moving too slow, and they just get trapped in the patient and cause damage. So we filter those out, just like a Brita on your faucet will filter out impurities. An aluminum filter filters out the long and low wavelengths. What it lets through are the short and high, and that's good. A rectangular collimator will shape the beam to be closer to the film size than the round one, which is 2 3/4 inches in diameter. That's the biggest it can be, the X-ray beam. And then a 16-inch PID, which we will see what that is in a second, minimizes the spread of the beam because X-rays start at a small point and they spread out. So a 16-inch PID will keep them from spreading faster. All right, so what does all this mean? Here we have our fast film and our digital. So remember, 20% for reduction of radiation for the fast film and 80%, 70 to 80% for the digital. And what is fast film? Fast film has bigger crystals in it than the D speed film. So F has larger crystals than D. And then when it comes to the X-ray machines, the collimator and the filter are right here in the machine. They're built in right here. The PID is this long thing that you point at the patient. And if you're, oops, I hate that it does that, I'm sorry. If your collimator is rectangular, you can see that there's only a little bit of radiation that's going to expose the patient that isn't useful or on the film, because this is the size of a film here. But if it's round, see how much more there is? Now, the reason that most dental offices still use round ones is because it's very easy to miss when you are using a rectangle, because that's the only margin for error you have. And so for most offices, the round is still in use. Even though the rectangular is better for the patient, this reduces how many films I have to take because I get it right the first time, most of the time. The PID is what you point at the patient. And the longer it is, the less spread of the X-ray and the less head is exposed. And this is a graphic of that. So the long cone, or the 16-inch PID, and PID stands for Position Indicating Device, reduces the divergence of the X-ray beam or the spread of the X-ray beam. So here is a long cone, or the 16-inch, and you can see that only a little bit of the patient's head is exposed. In this one, much more of their head is exposed. Now, it doesn't look like much when it comes to how much is exposed there. But in this one, you're going to end up with more of the blood-forming organs than in this one. And so that's a major savings to the patient to use the 16-inch. So what does doing this do? It reduces the intensity of the X-ray beam by 1/4 when we use a longer cone. And this is called the inverse square law. It's a math law that makes everyone cry. So I always say that if I'm using 16, I am 1/4 as intense. If I'm using 8, 4 times as intense because it involves flipping a fraction and stuff like that. That's why it makes people cry.
Inverse what law?
Inverse square law.
Okay.
Yep. Some additional measures that we use to protect our patient are to hold the film if the patient's unable to hold it. So you want the caregiver or the parent to do that. You never do that. So dental assistant never holds the film. Either the parent holds the film, or if it's an adult who is unable, a caregiver holds the film. All right. So many times I've had patients in wheelchairs who are unable to bite properly on the film holder. So they would have to hold it with their hand, but they're unable to do that as well. And so a caregiver has to come in. Both caregiver and patient have the lead apron on, and the caregiver will hold that while the exposure is done. Yep. And the reason for that is that if you do it, you're going to get multiple exposures because you're going to be doing it for every patient you need to, right? Mm-hmm. But if the caregiver does it, that's only one exposure for them. So for most RHS questions, the reason that we do anything is to comply with ALARA. And ALARA means as low as reasonably achievable. And it is the reason why we do anything, basically. So why do you use fast film? Because it's better for the patient. Why do you use digital? Lowers the radiation to the patient. All right. So and almost every time we ask a question, the answer is to lower radiation to the patient. All right. So if you're an operator, how do you protect yourself? The first thing we do is we wear monitors. They are not legally required in most states, but they are suggested and useful. So many doctors will have you wear them anyways. And what a monitor is called a dosimeter or a film badge. And it is warm at your waist while you are working. And what it does is it measures the exposure that you get throughout the day. So if I wear my film badge for a month and it comes back with exposure on it, then I know that I'm doing something wrong that I need to change because I shouldn't have any exposure because I'm not the patient.
So you have too much exposure.
Yep. So, yep. So it can't prevent exposure, but it can let you know that you're doing something wrong and that you need to switch it up. Now, of course, you also have to treat your dosimeter properly. You can't wear it outside the office because it will respond to sunlight. You don't wear it if you're having an x-ray taken on yourself. You don't leave it in your car. Do you want to know why they have a list of things that you shouldn't do? Because everyone's done them. All right. So I once walked around with my film badge in my pocket of my pocketbook for a whole summer. So can you imagine what my exposure was? Yeah, no. So happens. Equipment monitors. Usually the state will come out and monitor the x-ray equipment to make sure it's not leaking. And that's usually done once a year. All right. So that's another way we protect our operators. Because remember, we're working around this all day. And we're not the patient, so we need different protections than they do. Your rules for being an operator, you never stand in the direct line of the primary beam. So you never stand between the tube head and the x-ray. You never stand there. You always stand behind a lead barrier or a proper thickness of drywall. So you should always be behind some kind of wall. Now, if for any reason you cannot stand behind a wall, you should never be closer than 6 feet from the x-ray unit, and you should be at a right angle. So if the x-ray is here, I want to be at a right angle to it, 90 degrees, and I want to be 6 feet away. Okay. All right? And if you do these things, the never, always, never, you will have an exposure of 0. All right. So anytime I go into a new office and I'm going to take an x-ray, I am looking for where am I supposed to be standing? What's the safest place for me to put myself so that I can take a film without exposure to me? All right, because you don't want that. ALARA in everything we do is the upshot of this. Okay. Let's see where we're at. Good. We are going to move on to the X-ray machine. So this is the part where you will feel like you're learning something that you're never, ever going to use. And you probably won't outside of using it to pass the RHS. So you need this information to pass the test, which then allows you to take the x-rays. So you are going to use it, but not forever. And so what I tell people about this kind of stuff is learn it once, take the exam quickly after you've mastered it, and forget about it for the rest of your life because you're not going to need it again after that. All right. So our first objective is to identify the components of the dental x-ray machine. Okay. And here they are. The tube head is right here. All right. So the tube head is A. The PID is B. Okay. The extension arm, is C. And the master switch is at D. All right. So what do these things do? The tube head houses the heart of the machine, or the tube. So the tube is inside the tube head. The PID is used to aim the x-ray beam at the patient's mouth. And remember, we said that this may be round or rectangular. The extension arm extends to reach the patient, and we want to fold this completely when it's not in use. So it's either extended to be taking an x-ray, or it's folded up and placed against the wall. This prevents drifting when we go to use the machine. So folding it up and putting it back, because it basically has coiled wires and springs inside of there. And then the master switch here is the power button to the entire machine. So we've got a power button. They look different on every machine. So it might be like this, or it could be down here underneath. And the control panel for the whole machine is located outside the room. So there's the control panel. So the control panel has knobs on it that allow us to control 3 different factors. So kind of like a radio, you can turn up your volume, your bass, and your treble, right? On an x-ray machine, you can turn up or down your milliamperage, turn up or down your kilovoltage peak, and turn up and down your time. So these are completely different things. Everybody knows where a volume button is, right? But now we're here at this late age in our lives. We're stuck with learning something like this, right? Like, oh, seriously, why didn't they tell me about this earlier? Well, because nobody cares unless they have to use the x-ray machine, right? And then there is the exposure button, which is what we press to actually take the x-ray. So all of the other things that we do are before the x-ray is taken. Mm-hmm. The last thing we do is hit the button to expose. Okay. All right? So the patient should be visible when you are hitting the button. Mm-hmm. So many dental offices have windows so that you can still see your patient, but you're behind a barrier, so you're protected. Mm-hmm. All right? When you press this button, there is a light that will light up and a sound indicator that will go off. So you hear a beep and you see a light, and that's how you know that an exposure has taken place. Okay, and this is what the control panel looks like. Just kidding. You probably will never see one of those. They're really old. All right, so modern machines look like this. And the only thing that we can adjust on a modern machine is the time. Thank goodness. All right.
It's just the time.
Mm-hmm. So I learned on a machine like this. Yeah. And I can tell you that I had no idea what I was doing every time I did it. And I admit that freely. I didn't know what I was doing. And yet they still gave me the certificate. Okay. Wow. So what I want from you is what every patient wants from you, is to be able to know that they're in good hands. So how did I operate this? What I did was I followed whatever was written up there. So somebody got smart and they posted a number that said, if you're taking it on a kid, set it to this. If you're taking it on an adult, set it to that. Thank goodness somebody was smart enough to do that, right?
Do they
Or
still
else,
do that?
yeah, well, they do, except they do it with pictures. And that's the great part.
Okay.
All right? So, are you taking an x-ray on a big person or a little person?
Yeah.
All right? You're going to select. Are you using regular film or a computer?
Oh, okay.
You're going to select. All right? Are you taking a front tooth or a back tooth on the top?
Okay.
Are you taking a front tooth or a back tooth on the bottom? Are you taking a bite wing, which is a different kind of x-ray?
Mhm.
Or are you taking a premolar? All right, so it gives you all of these options, and every time you select, the time changes. All right, so you don't even have to do the up and down to the time. You're changing the time just by telling it what you're doing.
That's cool.
All right, so it is easy to set these now. What is not easy is learning why they are the way they are, which is what RHS still requires of us. So there are two things to think about here. There is the you that has to pass the RHS exam and the you that is going to do this in real life. All right, so the you that's going to do this in real life can do this now. All right, this is an easy thing to do. The you that has to pass the RHS has to get over the hurdles, and that's the hard part. All right, so when you get stuck on these things and you start feeling like I'm never going to be able to do this, remember me, okay? And who last week you guys couldn't hear me because I had the mute button on. All right, so you do not have to be a brain surgeon, my friends. All right, you just have to not quit because you can do this. All right, so during the X-ray, you get an audible sound, and then to make the X-ray happen, you hit the exposure button. And remember that this is outside of the operatory. So down here, you can see that this machine is set to 65 kV and 7 MA. All right? So I don't even have to do anything to those two values. Those knobs are already turned for me. The only thing I have to do is tell it what kind of X-ray I want to take.
Press the button.
Yep.
and that's it.
Yep. All right. So now we're going to get into the pieces of each part of this X-ray machine. So the tube head, as we said before, holds the tube. It holds the heart of the machine. The tube head is made of metal, and it has a lead lining to make sure that any radiation does not escape. So if you haven't picked up on that already, lead blocks X-rays. All right, and that's why the apron is made of lead and why the machine itself is made of lead, so that the X-ray only comes out where we want it to. So we direct it by lining everything with lead to where we want it to be. Most tube heads also have controls right in the dental operatory, everything except the exposure button, so that you can set everything before you run out of the room to hit the go button.
Cool.
Yep. So, all right. Let's look at the tube head itself. The tube head has, as we've said before, a collimator. And what the collimator does is it controls the size and the shape of the X-ray beam as it leaves the tube head. So the collimator is made of lead, and it is going to let through a certain size of X-ray and a certain shape. And so the size of the X-ray is probably 2 3/4 inches, and the shape is round. It could also be a little smaller and rectangular. Which one's better for the patient?
The round.
The rectangular's better
Oh.
because it limits the skin exposure.
Oh, that's right.
But which one do we end up using most of the time? The round, because it makes us more accurate. So there's a little twist in the question there, right? Which one is better for the patient? The rectangular is better. But which one are you probably going to see? The round one. Okay? And then inside of the tube head, we also have the aluminum filter. And the aluminum filter takes out the long and low, removes those ones that are moving too slow, and it leaves behind the short and high. All right, lets the short and high act on the patient. How thick is this aluminum filter? Depends on the kV of the machine. So in a machine that has 70 kV, below 70 rather, it is 1.5 millimeters thick, this aluminum filter. If the machine is above 70, it's 2.5 millimeters thick. And so I'm going to ask you a question. The kV on the machine here is 65. What is the half value layer of the aluminum disc?
35.
The half value layer is either going to be 1.5 or 2.5.
Oh,
Which one do you think it is?
1.5.
1.5, because
There's
it
less.
is below 70. All right, so the amount of filtration I need in a machine below 70 is 1.5. If my machine is above 70, it's 2.5.
Oh, okay.
Okay, so this is how they figure out how much aluminum do they have to put in there.
So that's a standard.
Yep, that's done by the manufacturer.
Okay.
There's nothing I can do about it, but I have to be able to answer it on a test,
Okay.
which is the unfun part. So, what's the filter doing? It is taking out those waves that are long and low. So if you don't have enough filter in your machine's going to let some of those long and low through, right? You don't want that because that's harmful to your patient.
Right.
So you want to be sure that you know how much filter it is supposed to have. Okay. The X-ray tube is the heart. And I had to put a heart in. And it is inside the tube head. The dental X-ray tube is made of glass. It's about 6 inches long and 1.5 inches in diameter. And there is no air inside of it. All the air's been removed. So when I look at this, I don't know about you, but it reminds me of a light bulb or maybe a battery, right? Something strange, right? And
Copper?
yeah, it is. Yep. And I never wanted to know anything about like electricity or anything. I was never somebody who thought that was cool. It was like, I like to switch. I don't care about any of the rest of it. Well, now we have to know, like I said, how the inside of this toaster works. So, this is what the inside of the toaster does, okay? Is it has one side, which is negatively charged, which is called a cathode. And at this cathode, you get a buildup of electrons, which are basically energy, all right? So you get a buildup of these negatively charged particles right here on the negative side of the tube. And when we hit the exposure button, these electrons take off, shoot across the inside of the tube, and slam into a target over here on this copper anode. And when they hit the target, they are changed from electrons into X-rays. So this is the point where all that stuff happens, where we make X-rays.
That's weird.
Yep, it is strange. Yep. So we make X-rays at the tungsten target. All right. And those X-rays then go down through an unleaded glass, through an aluminum filter, through a collimator, and out the PID to be pointed at the patient to create the X-ray, the film, the radiograph, that thing we're trying to take. This whole process makes a lot of heat. So this whole thing heats up really hot, and the copper is there to draw the heat out into the oil. So the whole tube here is surrounded by oil, and it draws the heat away from the working parts and towards the oil. It's kind of like a car engine. The oil cools everything off so that the car can run, and that's what the oil does here too. Doesn't that look like a radiator?
Yeah.
Right?
It does.
Mm-hmm.
Yeah.
So all this is a machine.
Like a car.
Yep. And when it was taught to me, I was like, what are they talking about and why? God, why? But what you really want to know is that electrons are made here by heating up a filament, like a light bulb, and then somebody speeds them up, and they go flying across the inside of the tube, and they make x-rays. And then those x-rays are harnessed and shaped and are pointed at the patient. And all of this happens within seconds when we push the button. All right? So we have to memorize the names of the parts because that's what we're going to be tested on. I know. You love me already, don't you? Okay. So inside of this presentation, and it will be posted on Evolve, is a blank tube. And you are going to practice labeling this until you can do it cold. All right? Until you can label each part and say what it does. That's one way to do that. Okay?
I take it this is in the book.
Yep, it is. And then there's also, here's all the labels on there.
Great.
Yeah, isn't that nice? Okay.
And you have to also tell what each.
Yes, what they do.
Okay.
Yep, their function. All right. So, and we're going to go through that again. And there's my hand-drawn one, which is maybe a little friendlier, but not much. Okay. And then there's labeled ones here with each one. So what I like to do, and I actually meant to hide this, and I will hide it when I go through to put it on, is I will hide the numbers so that you can quiz yourself. You can go through here. And with the same with this one. Okay, so, and there's just more of them. All right, so let's talk about the process and what happens. All right, so when you come into the office in the morning, you are going to turn on a master switch, and that is step one. When you turn on the master switch, the MA selector controls the number of electrons that are going to be released by the filament at the cathode, the negative side of this tube here. And this happens the whole day long. These electrons are just sitting there, they're dancing. That's all they do. All right? They're having a party, they're having a nice time. Somebody comes along, the cops are here. And the electrons go flying across the inside of the tube. They're like, no! Right? And they slam into the other side of the tube. And they turn into x-rays. Now, some of them get away. All right? And they escape out of the PID, and they are aimed at the patient. But some of them take the heat. And they are brought out through the copper and into the oil. And this is how the process works.
And they turn into oil.
Yeah. So the oil just absorbs the heat, kind of like for frying.
Okay.
In the same way that it just absorbs the heat. So the KVP selector tells those electrons how fast they're going to move across the inside of the tube, whether they go fast or they go a little bit slower. All right. So it controls the speed from cathode to anode. And when the exposure button is pressed, the indicator light lights up, the electrons shoot from anode to cathode, they collide with the target, X-rays are made. The X-rays are called Bremsstrahlung, which is a German word that means breaking, and the collision makes heat, and the heat is drawn into the oil by the copper stem. X-rays need filtering to make them safer, so the aluminum filter removes the long and low wavelength. The short and high are then shaped into round or rectangular and allowed to escape where they are shot at the patient. For a certain amount of time. And that amount of time is set in 60ths of a second, or impulses. So when we're setting our time, we're setting impulses. Okay. So let me do this. Because I have a link. Actually, let me not do that. Because I don't know where it is, but I've got it here. Okay. So let's look at this process for the inside of the machine. Am I doing on time? Good. All right. So here's the X-ray tube. And here are the buttons that I can use to control it on the control panel. All right. And if I put my KVP way up high and I put my MA way up high, I get a lot of electrons. That's what controls the electrons, is the MA. And the MA is telling them to go really fast. It's saying high speed here. Okay? What happens is I've got this strong X-ray that's created. Many of them. And the image that I get is going to have many shades of gray to it, be a little bit low contrast, and be a little bit dark. What happens if I tell them to go slow, but I still have a lot of them? So here my electrons are still partying, but it's a slow dance. So they're all clumped together here in the middle of the dance floor.
Okay.
I do not get
A lot.
a lot. There are still a lot of them, but they're not very strong, are they?
Okay.
So there's many X-rays, but they're not real dark black. And this is what the X-ray looks like. And this X-ray is still too dark for me to really read, but it's got a lot of black and white in it. Doesn't have a lot of gray. In this instance, half the people have left the party. Now, I don't have very many people left at my party, but the music is still thumping. All right? They are jamming out. You got to make it fun somehow. All right? And what I get are fewer X-rays, but they're all very strong. And my image looks too light, but has some gray. It's pretty gray, isn't it?
Yeah.
Last case. Nobody at the party. Slow dance. All right? Only a couple people have stayed. It's very late.
Low energy.
Yep. So low energy and not very many. Low energy, not very many. And what I get is something that's still too light, but is more black and white than anything else. Not a lot of gray. All right? So the ideal image is somewhere in the middle, somewhere between really high energy and really low. So where do I want to be? Right there in the middle. I don't want to be up here with either one, and I don't want to be down here with either one. I want to be somewhere in the middle. All right, and so this is what an image should look like. This has some shades of gray, but it also has white and black. All right. And we're almost done, folks. Sort of. Okay. All right. So there are 4 factors that control the way the image looks on the film. And these are basically 3 of them are buttons or dials on the control panel. So there are 3 things that you can do to set them. Those 3 things that you set before you press the exposure button are the MA, the KVP, and the time. MA controls the quantity of electrons and then the quantity of X-ray. So that's how many. KVP controls the penetrating power, or how fast they're going to go from one side of the tube to the other. And we say that's quality. Time just controls the length of time that they are made for. And then, of course, once we're all done with this, we document. We say that the patient was informed about how many X-rays they needed and the risk, the number and type of radiographs that we took, the reason we took them, and what we got from the X-rays. So when you go and you have an X-ray taken as a patient, they don't often explain the risks and benefits. They assume that we know them, don't they? And so you will too. But you will run into that patient every now and then who wants to argue with you about whether x-rays are safe. And that is also what this information is giving you, is some ammunition about how to talk to a patient about x-rays. So what will you say? You will say the benefit of having the x-ray outweighs the risk of not having it. All right.
Short and sweet.
Yeah. Okay. And that is the end of this one. We're going to go on to the next one, which is a lot shorter, and just has to do with things that we have already covered for the most part. Just a couple things. All right. So we are beginning to talk about what the actual x-ray looks like. We spent most of our time tonight on safety and on the dental machine. All right, so how to keep x-ray exposure low both to the patient and to ourselves, and how that silly machine works, okay? What we are going to look at now are the actual films and what their characteristics are, all right? So anything that appears black on an image is called radiolucent, and I have some mnemonics highlighted for you here, and those things that appear black on an x-ray are air spaces, soft tissue, dental pulp, and abscesses. Anything that appears white in a dental image is called radiopaque, and radiopaque is metal, enamel, and dense bone. Everything else is gray. So dental decay, dentin, and composite fillings are all gray. And we're going to look at these. All right, so here I have radiopaque, which is white. Mm-hmm. And so my choices for what this must be are either metal, dense bone, or enamel. What do you think it is?
Metal.
Metal, yep.
It's a filling.
It's a filling, all right? In B, this is the radiolucent. My choices here, excuse me, are either soft tissue, airspace, pulp, or abscess.
Yeah.
What do you think this is?
Soft, it's the tissue.
All right, soft tissue and air.
Yeah.
Because the patient is missing something here, right?
Yeah.
So here's my radiolucent is black because it has an L in it. Mm-hmm. Gray is gray, LOL. And radiopaque ends in E, and so does white. And this is how I keep those straight. Because you're going to get questions on that, and so you want to have a really fast way of remembering what the difference is.
I don't get what you're doing.
Okay, so when someone says, what color is radiopaque?
It's white.
Okay, but if you don't have that in front of you, maybe you forgot.
Right.
And so white ends in E, so does radiopaque.
Okay.
So they go together.
Okay, yeah.
Does that make sense? That's just a way to remember.
Yeah, that
Yeah.
makes sense.
And for this one, radiopaque does not have an L in it, but radiolucent does, and so does black.
Okay.
And so I can remember that black goes with radiolucent.
Okay.
Because many times when people are learning this, what they do is they screw up what's radiopaque and what's radiolucent. And then you get the question wrong. But not if you have this mnemonic.
Okay.
All right. Okay. So anything that is thick, hard, or dense is going to block x-rays. And that is going to show up as white. Anything that is soft or absence of structure is going to allow x-rays to pass through. And that's going to show up as black.
Yeah.
And anything in between is gray. So what's what? Just as we said, this is just a review of it to sort of drill it in. So black is air, soft tissue, dental pulp, or abscess. Gray is decay, dentin, bone, some bone, and composite. For white, metal, like amalgam or gold, enamel, and dense bone are all going to be white. And so when we talk about factors that affect the quality of a radiograph, we are talking about contrast, density, detail, and distortion. Detail means how fuzzy is it or how sharp is it, and distortion means like those carnival mirrors.
Yeah.
Is it longer than it should be? Is it shorter than it should be? Is it wider or is it skinnier? Okay. So density refers to how dark or light the overall film looks. So overall, this film is too dark. Overall, this film is too light. Okay? That's density. Contrast refers to the range of shades of gray between black and white, or how two things look different from another. So we have grown up, most of us, being assigned papers that say compare and contrast, right? And you all go, oh, right? I have to write a paper saying, well, this is like this, but that is like that.
Yeah.
Well, contrast, if you say it in a different way, if you say contrast, it means the same thing. It's how two things are different from one another. And so if there is a lot of black and white in a film, we call that high contrast. But if almost everything looks gray and it's hard to tell one thing from another because it all looks gray, we call that low contrast. So you can see that in this picture, the enamel, this big blob of white doesn't really look much different from anything else around it. Now, you can certainly still tell the difference, but it doesn't have a lot of sharpness to it like this one does. Okay, so density is darkness or blackness. Contrast is the range of shades of gray between black and white. And for contrast is controlled by KVP. Density is controlled by MA and time. So you can control how the X-ray looks by changing the settings on your machine. So remember, MA is a knob on my machine, and I can change the setting to change how my X-ray looks. Contrast, I can change the KVP to change how my X-ray looks. Now remember, we said on modern machines, MA and KVP are set.
Yes.
So what's the only thing we're doing?
Time.
So you will never actually change the density of or the contrast unless you turn up the time for density or turn it down. That would be the only way. Yeah.
Wow.
Only way you'd screw it up is by changing the time too much. However, we still have to know, I know, trust me, it makes me crazy too, but we still have to know how to change density and contrast. I don't know why. Don't ask me why. Don't shoot the messenger. Okay, so I have a mnemonic for this, like I have mnemonics for many things. So, if you're turned up, you get freaky, or 50 Shades of Gray, all right? And so that gives me low contrast and high KVP, because low contrast is gray. Remember, lots of gray, and turned up means my high contrast KVP. If you're turned down, you get reality. That is black and white, all right? Which means high contrast, because we've got either it's black or it's white. There's not much in between. And low KVP. And if you really get into this and make this make sense, this will help you to answer questions. Because they will say, the dentist would like you to create more contrast in the x-ray. What do you do? So how do you get more contrast?
You turn up the KVP.
Opposite, you turn it down. I know. So that's why we need the mnemonic, is because it's really hard to do this quickly. And remember, you've only got 75 minutes for those 100 questions. So you want a couple of quick mnemonics that make sense. If you need instructions on what turned up and 50 Shades of Gray is, I will refer you to Netflix. All right. So contrasts are the steps, or how many shades are in between the black and the white. And this is just another way to help you understand it. I had a really hard time with contrast when I was learning this. And that could be because I'm not much of an artist. So it all depends on your background and where you come from. So you may need, extra work on this. And then the contrast and density, we looked at how that works with the X-ray machine, and the link is there to go back and look at those what happens when you turn that KVP up and what happens when you turn the MA up or down. All right. So other factors that are going to affect how dark a film or how light a film will look, density, is how far away the X-ray is from the patient. So if your tube head isn't right up against their face, if it's way over here, you're going to get a lighter film. Amount of radiation that reaches the film, patient thickness. So if you have a really a guy with really thick bone, you may need to turn up the time because it's going to need to go through there a little bit better. And then if you're working with film, processing time and temperature also make a difference. For image distortion, if a patient moves during an exposure, you're going to get a blurry image, which we say lacks detail or is not sharp. If there is a long distance between your tooth and your film, you are going to get something that is fuzzy or distorted. And you also want to have your tube head to be far away from the tooth to avoid magnification. So if you're closer to the tooth with the tube head, if you use an 8-inch instead of a 16-inch, you end up, the tooth looks bigger than it is. So you know that thing like on your mirror that says objects are larger than they appear? That's what will happen if you use a shorter PID. Okay. And so here is a representation of that. You can see that we've got the shorter PID here and the longer one here. And so the one that's in this purpley or bluish color is bigger than it should be, all right, because the shorter one being closer to it makes it bigger. But as you get further away, it begins to look more true to life.
So it gets smaller
as you go further away. And you can do this, you can practice this at home with a flashlight in a dark room and little rabbit foo-foo. Yeah. All right. So you can take your flashlight and you can see that if you hold it close to your fingers, they're going to look like monster fingers up there on the wall. Really? But if you pull it back, they will begin to get smaller. And so it's a really good way to teach yourself about objects and magnification. Yep. So on page 212 in your textbook, it gives you absolute directions on how to try this with a flashlight and your fingers. And I mean, everybody's got a flashlight on their phone, true? Mm-hmm. So yes. Do this. It takes 2 seconds, and it really makes sense to you. Okay. So what do we want? We want to have the source, which is the anode inside of the tube. Okay. We want to have that be long, 16 inches. All right, we want it far away from the tooth. We want the tooth to be really close to the film. All right, so these two things, the O, your object, and your film, your F, should be close together. But your source, your S, should be far away from both of them for the best image. The last bits of this, just repeat this in a different way. Okay, so if you read back through this, you say you want a short distance between the object and the film for a clear image. If your distance between the film and the tooth is long, you're going to get something that's blurry. You want a source to film distance that is long so that it looks more true to life. If your distance between the source and the film is short, you're going to get magnification. It's going to look bigger. And so I am basically just saying the same thing over and over again in a different way. okay? Because it's important to be able to grasp both ways. So the quality of your x-ray, or how diagnostic your x-ray is, depends on contrast, density, detail, and distortion. And those 4 things you control as the radiographer. Okay? And that is all I have to say about that.
Contrast, density, detail, and
Yep.
distortion.
Yes. So, let's see. I know that you can't really read this, but at some point, I don't think I'm going to do it tonight. I bet your heads are probably full. But I would like to do a little bit of a round robin with everybody and go through some questions just to hear them spoken, because I think it's important to speak it. So, so maybe next time we'll start with a couple of these questions as warm-ups to get us back into this. All right. So, what's your job between now and next week? Your job is to read chapter 16 and to practice the inside of the tube head, practice labeling what's inside the tube and all of the parts and pieces, and to go back over these PowerPoints. If you think you're ready to take chapter 15, you can. But I would say do some practice. Be really ready before you get there. For chapter 15 and 16, the tests will not reset after you take them. So your first grade will be averaged with your second grade. So if you get a 40 on the first one and 100 on the second one, you're still stuck with a 60. All right? So you really want to be in a good spot before you try to take the test, okay? Because it's different than the other tests because this is a certification exam. Questions?
Yes, you said practice the tube. What else?
What's inside the tube head. So labeling that diagram. Yep.
And was there anything else? What's inside?
And just read chapter 16.
Okay.
Yep.
So to know
Yeah.
if we can answer questions.
Yeah. All right.
That's good.
Anybody else? Anybody freaking out?
I am.
I know.
I am too silently.
It is. It's overwhelming. That's a lot of stuff. It really is. I don't expect that you will learn it all. Yes, go ahead, Joelle.
If you do 15, like, let's say if I had like a 60 on 15, does that
reset yours. I reset yours, honey.
Yeah.
So the grade is still there, but as soon as you take it, your new grade will go in. Okay.
Okay, and what's the average grade like above on the right hand? Is that our grade overall throughout the class?
Yeah.
Yes. Yeah.
So,
So-
Does how we're passing is that low grade above? If we know
So-
we're passing or not?
You want to the average grade that means that you're passing. Yes. Yeah. And you're fine. You're fine.
Alright.
Yep.
so is the grading like a regular scale, like 90 to 100 is
Yes.
an A?
Yeah.
Okay.
Mhm.
Okay.
Yep.
So I'm at a C right now.
Yeah.
That's okay.
Who's missing in Turner? Who's missing?
I want to be though.
Liza just went home.
Oh, she did. Okay, but she was there. All right, because all right. I thought did she come last week? She's not answering me. I didn't think so. Thanks. All right. Anybody else want to cry with me? No. All right. Okay. Have a great night, everybody.